Today's lesson will be on distance formula. The distance formula really comes from Pythagorean theorem. So just as a quick refresher from what you've seen in middle school on Pythagorean theorem, you're given, let's say you're given you wanted to find the distance between these two coordinate points, which we'll call A as x1, y1, and B as x2, y2. And really, distance is the same thing as the length of the segment. So if I actually fleshed out a triangle from this by adding in the legs of this triangle, I can really use what information I know about Pythagorean theorem to derive this formula for distance formula. So let's begin with what is Pythagorean theorem. Pythagorean theorem said that if I knew the length of one of the legs being A, the other length of the leg being B, then I can find the hypotenuse by using the hypotenuse being C, by using the formula A squared plus B squared equals C squared. And we knew that this worked for any two sides, whether you're given two legs or a leg and a hypotenuse, and allowed you to find the third side so long as you had a right triangle. So here, instead of A, B, and C, to develop the distance formula, what we're going to do is somehow relate AB back to x1, y1, and x2, y2. So following my spotlight, you guys can see here that the distance between, or the length of this leg, is really the change of x. That if I started here at x1 and then I moved here to x2, I've now moved a total of x2 minus x1 distance. So A can be redefined as A is the change in x, so x2 minus x1. Whereas if I look at the length of the leg B, right here we have a y value of y1. Up here we have a y value of y2, so this change here represents the length of leg B. And we can find horizontal and vertical length simply by finding the difference. So B we can define as y2 minus y1. And lastly, once we have those two pieces of information, we can find the missing length of the hypotenuse, which is the distance between A and B, and also called C. So now putting all that information together, what I'm going to do is replace A first as, and I'll do my work over on this side. I'll replace A with x2 minus x1. So let's go ahead and replace A with x2 minus x1 quantity squared. I'm going to replace B with y2 minus y1. So we get plus y2 minus y1 squared equals c squared. And c squared is, in this picture, ab squared. Actually, let's do that substitution as well. So it's what we're trying to find, ab squared. And if I solve for AB to get AB by itself, I can undo squaring by taking the square root of both sides. So that my distance formula, the length of AB, can be defined as the square root of the change in x, x2 minus x1 squared, plus y2 minus y1 squared. There's certain things that you learn where I'll tell you guys it's super important for the rest of the course, plus any other math classes that you take after this. So this is one of them. The distance formula will appear again and again throughout this course, as well as into your future math courses. So let's do a few examples. We're going to do example 3. First, I'm going to say that if I didn't have the picture on the right and all they provided for me was the two coordinate points, I'd probably just use distance formula to start this problem off. But some people adapt the distance formula from their knowledge of Pythagorean theorem, and they simply flesh out, and you can do, like if you had the graph of segment AD, and we're going to do this example here, segment AD, you can find the length of this leg and the length of this leg to then just use a squared plus b squared equals c squared. So you're essentially doing that, the math of the distance formula in your head. But if I were just given the coordinate points and it wasn't plotted for me and I didn't have that visual, then I most likely would rely on the distance formula itself. So the length of AD is equal to the change of x. So we begin with the change of x. We pick one of the x's to start with. So let's say I picked 3 minus a -1. So the change is the difference between the x's. And then I would find the change in y. So because I began with the 3, I'm going to go ahead and begin with the -5. -5 minus 1, so change in y squared. And now simplify inside that square root. So inside that square root, 3 minus a -1 is 3 plus 1, or 4. 4 squared is 16. -5 minus 1 is -6. Quantity squared is plus 36, equals square root of 52. And then we want all our answers to be in simplified radical form unless it asks for a decimal approximation. So if you recall, simplified radical form meant that you can't have a perfect square inside the square root. So what you want to do is break apart 52 to be 4 and 13. So formally, the square root of 4 is 2. And so our answer is 2 radical 13. 13 is as simplified as you can get inside the radical. Informally, I think I do this with my Algebra 1s if they have trouble with radicals. I describe to them the square root is a house. The house is in a dangerous neighborhood. It's kind of just a silly story to think of a way to help kids remember how to simplify radicals. 4 is the same thing as 2 times 2, and then we have the times 13 to get to our 52. So in this house, in order to escape this, the house, you would need a partner to leave the house since you're in a dangerous neighborhood. So we see that 2 has a partner. So one of those 2's can leave. So the circle 1 can leave. The one that I crossed off, unfortunately, when you guys were trying to escape the house, he died in the process because it's a dangerous neighborhood. So that one of the 2's gets to escape, and what we're left with is the other 2 is gone, and then 13 stays inside the house because it doesn't have a partner. So just a silly way of thinking of how to simplify radicals. Now I'd like you guys to try finding AC. Your answer is going to have a square root in it. And so when you're entering it into PlayPosit, the answer, I'll have the word SQRT to represent square root. And then you just tell me what value would go inside here would be the input that you put there. So for congruent segments, this next section is just talking about what congruent segments are because we just talked about lengths of segments. Two segments are congruent if we can conclude that they have this equal lengths. If two, and then it's converse, if two segments have equal lengths, then our conclusion is that they must be congruent. Then they are congruent. So for example, if you knew that without the marker on top of a segment, the segment notation like that, we would say it's the lengths of the segments are equal to each other. So the length of AB is equal to the length of CD. Then our conclusion is that AB is the segment AB is congruent to segment CD. So if we're going to use this congruent symbol, we want to make sure we use these segment symbols on top. Let me undo that. So in example number 3, is AC congruent to AD? So go back to your calculation of AC, compare it to AD, and if you can answer, are those segments congruent to each other? And then for part B, if DE is congruent to AC, so if DE is congruent to AC, then DE is equal to, the length of DE is equal to, and then go ahead and fill out the answer. Again, with the assumption that your answer has a square root in it and that you're fill in the blank spot, you're just going to fill out the answer for that.